All right. Okay, I'm just gonna get started. Hi, everybody, and thank you for coming for the IVM tutorial session. In this case, we going to have, or we are having, Thomas Prisner as our speaker today. And now, of course, we know him quite well as he has paved the way, as he would describe, for the last 4 decades. And so his tutorial will pretty much comprehend, or he will, as the title suggests, reflect on and projections on his last 4 decades of where the field has been, where it is now, and where is it going. Now, Thomas himself, he has been at the Frankfurt University for a long time. When did you start at Frankfurt, actually? That's a good question.
1996.
1996. So ever since, he has paved the way. So, which comprehends biological EPR, DNP, method development, um, machine development, for that sake. Anything else that I'm forgetting? I'm pretty sure you had your fingers in all kinds of developments. So I'm excited to hear about it, and therefore I give the stage to Thomas Prisner, and please take it from there. Thank you.
Thank you, Thomas, for introduction. Let's see. So I hope you can all see my slides, and let's see if I can have a pointer. Do I get a pointer here? Okay, good. So welcome to my talk. When Thomas asked me quite some time ago to give a presentation here, an overview presentation of an old guy in EPR, then I had a couple of different titles in mind, but finally Thomas convinced me to talk a little bit about instrumentation, which might not be the most exciting topic, but I think for EPR still most important, or let's say at least I think a very important topic. So as I heard already in 1996, and that was not the start of my career, of course. So the 4 decades are really serious and actually strange to say. Now, in 40 years in magnetic resonance, or more than 40 years, you do a lot of things, a lot of crazy things, a lot of strange things. So finally, I figured some of them are connected, but I want to concentrate today on 2 aspects. One is high field EPR, and one is shape pulses in EPR. And you can even combine that. We will see that. And of course, connected to high field EPR, for me at least, is also a DNP. Because you will see in the presentation, I will also talk a little bit about DNP, because I think especially for young EPR community, it's important to see how important EPR is for further optimizing this very vivid field in NMR. So just to show you what 4 decades mean, so I started my diploma thesis in Heidelberg in medical, I did my diploma thesis in the Max Planck Institute for Medical Research, Molecular Physics, with Karl Hauser. And actually I started with ODMR, so optical detecting magnetic resonance there. But then I think in the first months when I was there were 2 guests invited. One was Jan Schmidt, and the second one was Bill Mims. And both of them gave brilliant talks about photoexcited triplet states, doing pulsed Endor, and the other one doing pulsed EPR on rare earth ions. And I was so fascinated, so I immediately switched to pulsed EPR and to pulsed microwaves, let's say, and to microwave detection. And then after that, I continued my PhD with Klaus-Peter Dinse, which I already met there and worked together there in the Max Planck in Heidelberg. And then the title of my PhD thesis was Coherent and Stochastic Excitation of Spins. You will see a little bit later on only one transparency out of it. But you can see Klaus-Peter Dinze, hopefully you also recognize him, hopefully you recognize me. So that was the starting of magnetic resonance for me. Now after that, after diploma thesis, ODMR, then switching to EPR, pulse EPR and PhD, and then I went to Bob Griffin's lab at MIT, and that was an eye-opener for me, I have to say. There he had just built it up, a setup for DNP at 5.0 Tesla, 140 gigahertz. And the microwave part was not working yet. The NMR part was not working yet. The two postdocs I worked together a lot was Sun An and N. McDermott. Sun An is now in Saclay. You might know him. He's doing a lot of very nice EPR on manganese, high field EPR. And N. McDermott is Columbia University doing solid state NMR and DNP. And that was our first start. You know, in the beginning, we had a magnet, we had a microwave bridge, but we didn't have the console actually connected to the magnet. So fortunately, there was a hole in the floor, and so we were running over 2 floors experiments by the phone to connecting NMR with EPR. Now, in this postdoc time, I just show you 2 transparencies, and that started all my interest in high field EPR and high field DNP. And at that time, we got the first DNP experiment running. This was a kind of unusual experiment. It's totally different from what Bob Griffin is doing now so successfully. But at that time, we didn't have a gyrotron running. And so what we did, we got a 330 watt pulsed EIO, extended interaction oscillator, from the plasma fusion physicist. But of course, it had only very short pulses and a very low duty cycle. So it was not good for solid state DNP, but it was working for Overhauser DNP. And I got actually, from my old connections, I got a one-dimensional organic conductors, which give a very nice Overhauser enhancement. So you see here, microwave on, microwave off. And so that was the first publication. More or less to please Bob, because Bob said you can do whatever you want if you have done one DNP experiment. So after that, I switched to use, and I think that was the very nice thing from Bob Griffin. From the beginning on, this spectrometer was supposed to also have a full detection of EPR. So he was totally aware that if you want to do serious DNP at high field, you have to be able to characterize the radicals at the same field. At that time, that was not usual. Yeah? So there were 3 high field spectrometers at that time running. One was from Jack Fried at 220 gigahertz. One was from Lebedev in Moscow, about, I think, 180 gigahertz. Bob Griffin, and then Bob Griffin's setup. And then there was all of them CW, and Jan Schmidt had a W band pulse EPR at that time already running, which was working at 95 gigahertz. So, but with this EPR, the EPR was really working very nicely, was nicely constructed from Militech, and a microwave company which is now in charge for also in the connection with the gyrotrons. So this was a very nice heterodyne setup with very high sensitivity after everything we got working. And then one of the first things which I did is, together with N. McDermott, we looked on the G tensor, the main G tensor values of the donor in photosynthetic reaction centers, cyanobacteria. So that's a P700 plus a chlorophyll dimer. And up to that time, that was not known, and that was a publication which got a lot of attention actually. And so after this, I went back to Frankfurt, not to Frankfurt, to Berlin, to do my habilitation in Germany. That's what you do. It's like an assistant professor or something in the United States. And then I was so fascinated about it. So Sun An went to Saclay and did build it up a high field spectrometer, and I went to Berlin and built it up a pulsed high field, a W band EPR ender setup. And you see from these early times, the spectrometer looked much bigger than they look nowadays. Yeah? So a lot of electronics, everything running by an Atari computer. Yeah, and the people which really helped to do that is Martin Rohrer, which you see here, and then Jens Störing for the computational side. And that's a microwave board which we built it. And this is the resonant microwave Endor probe, which has also light excitation. As you can see, a fiber is going in. And so what we explored and what you have already seen before at high field, of course, what is high field EPR good for? So high field EPR really started at that time. At that time, there was no commercial high field EPR machine. There was actually not even a pulsed EPR machine yet. And what was really fascinating is that for many organic radicals, of course, you can really distinguish them now by their G tensor, like here for a quinone molecule. So you measure all the three components. And then with that, of course, what you can do is now with pulsed EPR, you photo excite, and then you do pulses, and then you just look on the spin correlated radical pair. So that's again a very early publication from this time, 40 years ago, almost 40 years ago. And with this polarized signal, so it's absorptive, emissive, and you can analyze it in detail. And then you get actually the geometry of this radical pair, the distance and the geometry. So this is very, very useful information, of course. And at high field, you can do this. There are experiments on this were done a long time already before Arnold Hoff and Stehlig and Lubitz and many people. But high field was really necessary to get all the detailed information, because otherwise these radicals, you cannot resolve any kind of orientation out of it. And so orientation selection, which means now here you go to one field position and then you only excite molecules with a specific orientation. So it's like you have not a single crystal, it's a frozen that was a frozen solution of these membrane proteins with lipids, and then but then with EPR, with the position in the field, you select kind of single crystals, small single crystals out of it. And because sensitivity is high enough, you can do this experiment with extremely well precision. And before, if you go to lower field, you can do this, but you have to go to single crystals. And then if you have single crystals, you make an X-ray, and then you are done. Yeah. So after Berlin, actually, this spectrometer, I think, started my career to get a professorship in Frankfurt. You see, this is application to photosynthetic reaction centers. And in Frankfurt, we have the Max Planck Institute for Biophysics with Hartmut Michel, the Nobel laureate for this for these reaction centers in there. So a lot of people got really interested in what can you do with EPR now on such systems. And so then I went to Frankfurt 1996, and then immediately Martin Rohre in the beginning there, and later on Vasil Denichenko, which you see here, which you probably maybe also know from conferences. And you see also Marina Benatti there. She was at that time a habilitant in my group, then coming from Bob Griffin's lab then to Frankfurt. And so we built it up a spectrometer similar like the one in Berlin, but a factor of 2 larger in field. So this is now 6.4 Tesla at 180 gigahertz. So a G-band spectrometer. And again, you see the microwave bridge, and you see the Endor resonator here with slits and with an Endor coil actually connected, and that's a capillary. So everything becomes very, very tiny, but still you can do so it's more complicated, obviously. So our spectrometer nowadays, this spectrometer is running for 40 years, and it's still running like a beauty. Of course, the reason is that Vasil is still around. Yeah, he is officially retired, but he will never retire. And so you can do a number of things that all of you know. I have seen Graham Smith is in the audience, so a lot of experts in high field EPR, and they know what to do with at high field. One of the beautiful spins you look, or let's say paramagnetic centers you look with high field EPR is half spin, half integer high spin systems like manganese. And here you see, for example, this is on a biological system. This is a manganese replacing magnesia in a P21 RAS G protein. And you see, if you go up with frequency, how the central transitions become narrow and how they spike up. And they become really so narrow The reason is that's it's only second order field dependent, and what it means is if the zero field splitting becomes if the magnetic field becomes large, then you suppress these second order effects, and finally you get a line width of a single manganese hyperfine line, which can distinguish actually from the surroundings. So you can distinguish if it is bound to a GDP or it's bound to a GDP. Yeah? You see immediately on the line width, you see immediately what's happening. And you can actually also distinguish if there is water bound, which has, let's say, you replace O16 by O17, and you see immediately the hyperfine broadening by the water, and you can even count it. Now, what Marina Benati did, she did also indoor experiments on that. At high field, you get beautiful. This was done on W band, and then you get a beautiful indoor spectra, and then you can really analyze the distance to the phosphorus, which carbon is coupling, what is the protein surrounding. So really beautiful. And now, another more exotic topic. This is a topic I think which is for general very important also for biological systems, that manganese works very well at high field. But a more exotic topic is if you go to high field and to low temperatures, then actually we get really a almost optical polarization of our EPR spin. This can be interesting for DNP, of course. Or it is interesting for DNP, yeah. So at high field, then you have at low temperatures at least, you have very high EPR spin polarization. Not as usually only 1%. You can go up to 50 or more than that. But it's also interesting for the classical EPR experiments. Many years ago, Andrei Marco, he was a postdoc in my group, he recognized that if you have this if usually we have these populations are almost equal. Yeah? So we have a difference, of course, otherwise we would not see a signal. But the difference between the alpha alpha and the beta alpha is the same than between beta alpha and beta beta in the high temperature approximation. Now, if you go to high field and low temperatures, this is not true anymore. And that means the two dephasing vectors for the alpha and beta manifold of the second spin, they don't have the same strength. And that means you not only get an amplitude modulation in Peldor, that is the blue line which you see here, but you get also an out of phase signal. Mike Bowman has also shown that, and others. And at high field, actually, Andrei Marco he looked into it, and you can use this if you analyze the data to get kind of rid of the background function. It's tedious because at these very low temperatures, the T1 is very long, so the averaging is very slow. But it's interesting from I would say from a theoretical point of view. And he has just shown how big this out of phase signal magnitude is. And so classically at Q band, you have to go to very low temperatures to make it sizable. But then if you go to G band, you get a really very strong effect. Yeah? And so this can be used, and we have actually some recent publication together with Stefan Stoll. This is a collaboration where we analyzed in detail these signals, also in the background signal, not only in the intermolecular, so in the intramolecular, not only intramolecular, but also the intermolecular contribution to this out of phase, which is very interesting. Yeah, because we see spins actually as big as the sample are. So the sample size even plays a role. Again, a little bit more exotic, but something which at that time we were very interested in. If you go to high field, you get this anisotropic G tensor, and you can do a Hahn-Echo decay. And immediately what you see is you get anisotropic relaxation, T2. Sergei Zuba did a lot of experiments on that at low field with nitroxides, where he has, of course, then the AZZ of the nitrogen tensor is you can use for that. And at high field, you can use all the three canonical orientations. And for example, for quinones bound in a protein, you can figure out what is the mobility at 100 Kelvin. 100 Kelvin is still not, it's still a glassy state. So there is still some librational motion. And then you can find out how is the binding of such a quinone, which usually gets replaced in membrane proteins in mitochondrial respiratory chain. And how are they bound when they transfer electrons? Are they bound on both sides? Are they bound on one side? That will distinguish in the motion which you see. So, but then, of course, one of the big topics which we use since that time is using orientation selection for PELDOR for dipolar spectroscopy. And the beginning was done again with Marina Benatti being in the group, and she had a collaboration with Joanne Stubby, and she looked on a ribonucleotide reductase dimer. You have two tyrosine radicals, and now if you do the PELDOR experiment at high field and you just sweep over the spectra, then you see beautiful here how the dipolar oscillation goes from the single frequency to the double frequency, and between you have the magic angle. So you get all the angular information. And this is amazing. For Marina showed that for such dimers, you can actually find the dimer structure just by looking on the PELDOR signal between the two tyrosyl. If you know how the tyrosyl are embedded in the protein, they are naturally in there. So this is beautiful. And now what we do, after that, what I did in my group for a long time, we used it for looking on nitroxides. Nitroxides which are rigidly bound to a protein or to an RNA or DNA, which we actually use mostly, and then using this orientation selective to get more than the distance out of PELDOR. If you think about it, so these are the spectra here, Q-band. At Q-band, the G anisotropy and hyperfine anisotropy kind of cancels, so you don't have orientation selection. So all what you get is the distance. Even if you have rigid spin labels. If you go to X-band, then of course the AZZ of the hyperfine coupling can be distinguished, and then you get the two out of planes. You get the angle between the two planes of the two nitroxides, and if they are rigidly incorporated, that means you get some information about your biomolecule. And then you go to high field, and in high field you get everything. But you have to do it step by step, because finally it's 6 parameters which you have to optimize, and you cannot do this in a single step. But Andre Marco, he found a very nice procedure how to do this, how to fit it, and how to optimize it. And I think we have a very good procedure, and our other groups also do this actually now. Graham Smith, Bela Bode, Olaf Schiemann, many groups. And also there are now other spins which are doing this, like Saxena's beautiful spins, Sunil Saxena's beautiful spins, the Kappa spins, which are rigidly incorporated. I just show you one application, and this is an unpublished publication. So application. It's an unpublished application. I think it's very nice, very beautiful. So it's a DNA zyme. So there is one strand DNA, and the opposite strand is RNA. It's artificial, but what it does, it with the right sequence, it will break the RNA strands at the catalytic site. There is one metal here, which is there can be a different two valent metal ions, and so if we have one rigid spin label in this double strand, we have one rigid spin label in this double strands. The rigid spin labels, they are all synthesized by Snorri Sigurdsson. Very nice spin labels which incorporate in double strands of RNA or DNA and are rigid like cantilevers in there. And now if you do Q-band, you see 3 distances for the 3 different states. The one state is without substrate. This is the green one, the distance distribution. Then the blue one, what you see is if you have the substrate, but you don't have a metal ion, so it's not reacting. So that is the blue, big shift in distance. And then the third one is the post-catalytic state when it is reacted. Yeah, and then you see again a different distance. So this is nice, but if you have the distance alone, you cannot really say something about structures. Yeah, and there is a structure actually for the pre-catalytic state. For this state, there is a structure which you see here, the X-ray structure embedded the spin labels. And now, if you do these experiments at high field, you see beautiful for all 3 states the orientation selection. Yeah, so all the states are well ordered, even without a substrate bound. You think this is a single-stranded DNA, it should be very flexible, but it's not like a worm-like chain. It has already a pre-structuring. And then you see clearly the differences. And then here, this is only shown now for the pre-catalytic state. If we look now, if we fit our data, then we get a bundle of possible structures. Here is shown the X-ray structure in blue. This is the one helix, the second helix. And then we see it's kind of distributed around it. Yeah, so crystal structures and as many others, they freeze, they show the average. Now, what we see is, of course, a frozen solution. But what we have shown with a lot of comparison with NMR and with molecular dynamics and other methods, that at this frozen state, we see very nicely a frozen-in ensemble, which is actually also active at room temperature, at least in the cases we looked for. And so this is very nice. So EPR is very strong. You know, Hashimi in NMR is doing this with residual dipolar couplings and with NMR dispersion curves, well, using NMR to look for this conformational dynamics for the flexibility, which is important in these RNA and DNA molecules. And EPR is a very strong complementary method to do that. And we look on a long range distances, and we can really measure something like that. And there are not so many methods which can look really for the ensemble. There's a big advantage actually to freeze the sample. If you go to room temperature, we have done one example where we did such an experiment in room temperature, and then we see just the average distance. We see much more oscillations, beautiful, but we lose actually the dynamic conformational space. Now, this was all done with this 180 gigahertz G-band machine. And then 2015, so this is already also 10 years ago, we got a further machine at high field. This is 260 gigahertz, pulsed EPR machine, Endor EPR machine from Bruker. You see here it was just set up, and here you see actually Igor Kromov from Bruker who was setting up this. So it was a dedicated instrument at that time. There are not so many sold of this, and it was a unique piece with having the opportunity to have shape pulses even at high field. And Graham is doing this also at W band, and I think there is a big chance to do something like that at high field, but not so many. It's not so trivial also to say. Just to show some examples, Dimitri, he's now with Bruker in Billerica, and he did experiments on manganese, doing Peldor or RITMI experiments. Actually, this is a RITMI experiment on a model compound, but he also did RITMI experiments on membrane transporters. Below you see measurements, Peldor experiments done at 260 gigahertz with trityl radicals. Now the microwave power in our setup is so low that even with trityl radicals, you don't excite at this high field the whole trityls. You don't do a double quantum experiment, you do a Peldor experiment, but the modulation depth is really weak. And then with the shape pulses, you can improve. There is a big improvement, but it's not as big as you would expect. And a reason of that is that it is very nicely working for phase modulation. Unfortunately, it's also not so trivial, but it's also not so nicely working for amplitude. You see this here, these pulses, they don't have the real shape which you really would expect to have for a shape pulse. You know, if you don't make an amplitude modulation, you get holes into your excitation inversion, and that is a little bit the problem. It's of course very difficult, because if you multiply your ABG pulses from low frequency to high frequency, it becomes very nonlinear in the amplitude, and then the dynamic range is very, very low. So here in the end, I have also two publications in red. Actually, we started with a number of publications. I have to say, the publication kind of stopped 2018, and the reason is the instrument was broken for a long time after that. I think now it's working again, but it took a long time to repair it. These high frequency setups, to be fair, they have advantages, but they are really complicated. And here it was going, I don't know, 20 times between Bruker and us. And fortunately, Karlsruhe is not so far away from Frankfurt. Now, at that time in the beginning, what we also did is, these are two papers which we kind of did a service for people doing solid state DNP. One is from Hartmut Oshkinat's group, and the other one is was from the people from Lyon and Oliver Quarry. And if it's for high field DNP, it's very, very important to know about the EPR properties. Not only where is your EPR line, but also to know the relaxation times and dipolar couplings if you have biradicals. So Bob Griffin realized that from the beginning on, and I think there is a lot of improvement possible if you have the opportunity not only to do your DNP experiment at a given field, but to do in comparison directly at the same field the EPR experiments. And so that is, I went the other way around. Of course, was getting interested because Bob's DNP was running so beautifully. And then we started also in Frankfurt to set up for the same field, 260 gigahertz EPR, 400 megahertz NMR. We started to set up an instrument, not for solid state, but for under room temperature conditions. Now, room temperature conditions, there is one big difference because, so this is the spectrometer, it's a gyrotron, and this is from Goethe, from Russia, and there is a classical NMR spectrometer. There's a microwave bridge, which is from Ukraine, from the Academy of Science, Microwave Technology, Ukraine, which is now out of work. Sorry to say that, yeah. And at that time, still 2007, there was still people from GAICOM from Russia working together with people from Ukraine. Nowadays, again, impossible, really sad. And this is a very nice setup. It's a Michelson interferometric setup, so you can in principle even measure the EPR signal under the gyrotron microwave conditions, because you just make an interference for the EPR detector. And this is a home-built probe head for, you see, NMR frequency is the coil, EPR is the cylinder, yeah? And this is the waveguide for the EPR connection. And I should say again, all this instrumentation, the probe is the most important thing for liquids, because if you don't have an EPR, a resonance structure for the microwaves, you will blow up your sample at room temperature and at high powers, yeah. And so Vasil did all this building of the probes, and we started with a T101 102 resonator for EPR, and this is a later version. This is a Fabry-Perot resonator, which has much more sample size and a better field distribution and so on. And a lot of development went into this. It's technique. It's a lot of technique development. But finally, if the technique is working, now you have this Fabry-Perot resonator, and then you can align your sample like a lipid with radicals in there. And then what we saw, we can even with lipids, we get decent DNP enhancements. Yeah, so we get for the protons of the lipid, we get enhancement of 15, 16. This is surprising. It's Overhouse enhancement. We were for a long time puzzled why this is happening, and now we understand it quantitatively. But I'm not telling about this application. But there are interesting applications also for Overhauser at high field. Marina has shown this a lot with carbon-13. This is protons. For carbon-13, you have also very specific system where this is working nicely. Now, Andrei Kuselev is an independent group leader now here in Frankfurt. And he found out very recently that if instead of, this is the EPR line, it's a trityl radical in these lipids. And if you instead, now this is in glycerol, and if you go instead of going on the central position, if you go just off resonance, as you would do in solid state, even if you have a liquid sample, you get beautiful enhancements of 45. No? So this is very funny. You get solid state DNP in liquid samples. And what is the story? Read the papers. But the story is, if you go to high field EPR, it might be a solid for EPR, and it still might be a liquid for NMR. Yeah? Our frequency defines what is a liquid and what is a solid. And if you have a big anisotropic G tensor, then of course we have a different case. We don't average out anymore so easily our anisotropies. And so you can have a solid effect even if it is a liquid for the NMR. And this works beautiful. This is all work from Andrei Kuselev. I just show you that also in this field, it's important to understand the EPR. Where is the hyperfine coupling coming, the anisotropic hyperfine coupling coming from? You can do high field endo for that, and he's going to do that. But it works for everything. You can do it with water, and you do it with a ATP, and then you get beautiful enhancement. All the enhancement are 50 or something like that. beautiful. So there is this is very, very new, and Andre is just applying now for a big grant for that, and hopefully he gets it. And I think this has a beautiful future, and EPR will play a very important role into that. I will skip, because of time, I will skip other DNP which we did at lower field. I will skip this and give you first a summary about high field EPR. So, you have seen 30, 40 years, 30 years, 35 years of development from my side. And I'm very sorry to say, of course, not only we did high field EPR, no? A lot of other people do it and did it. But I show examples from my lab, and of course there are many, many others. So my summary is you get higher absolute sensitivity, but and if you do it like Graham Smith with his large oversized, not a single mode resonator, you get also higher absolute sensitivity, means spins per Gauss, and concentration sensitivity is spins per Gauss per volume. And Graham showed beautifully that you can even there win dramatically. But I think the backside is it is more complicated. So you have to think about what kind of application. What do you really you should not use high field if you can do it at Q-band. Q-band is not high field. Half integer systems are very nice. The central transitions becomes very narrow. You become very, very sensitive. You will see even small backgrounds. It can also be disadvantages. If you go into cells, you see always manganese at high field. The resolution of the anisotropic G tensor for organic radicals, that means also amino acid radicals, is very, very beautiful. We have also some joint publications with other groups now where we could really disentangle. There was a wrong prediction about what radical plays a role in collagen, and then with high field EPR we could just immediately show what it is. Yeah, and this is important. Yeah, for assignment. It's an assignment question, but you can also use it, of course, for orientation selectivity, and that's what I like a lot. Yeah, endo of low gamma nucleus. Yeah, if you go for nitrogen or something, then of course you have to go to high field. And what is also interesting for EPR, but also for DNP, is you have a high spin polarization, of course. There is a connection to DNP, and I think what is also interesting is that this dynamics where high field EPR is sensitive to, and where Jack Fried made very, very early contribution and work to, that is also something which can be used actually. Now, I think what will happen in the future, NMR is going to 1.2 gigahertz. This is S-band. So EPR should follow, I think. And this is difficult. It's not so easy. And if you want to sweep such a magnet, this is difficult either. But Petri Neugebauer and others, they are doing now this frequency sweep, very high frequency EPR. That is a really good alternative. Then you have to think about, of course, about not having standing waves. Yeah? But I think there is something to think about, because DNP is going to higher field, and then EPR has to go to higher field. And you can think about in-cell applications. For real cells, they are very tiny, and to sort them and to have a big sample is difficult. But because you have this very high sensitivity for small volumes, that is something where high field EPR should go to. In principle, if you calculate the sensitivity, you should be able to look on a single human cell and on paramagnetic centers in there with high field EPR. And I think one field which is, for me, clearly EPR, but has a big outreach, is pulse DNP. So Alexander Barnes and others, and Genevieve in Constance and others, and Bob Griffin are doing that and thinking about it. But the tricky part is switching microwaves, and you might also want to have then arbitrary wave function generators, shape pulses, and high power and good switches. And this is EPR pure. Yeah, so you have to understand about the spin dynamics of the EPR spin. So there is a big future of high field EPR. Bruker didn't sell so many 260 gigahertz spectrometers so far. I think it's now the fourth instrument which is going to the United States, just in Karlsruhe sitting and being tested. But of course, one of the problems is the reliability, because you know, if you the probe head, you have to have probably some capability to repair some at least microwave resonators or parts in your own place. Otherwise, it's becoming really time consuming. So it still means it's not really pure application. You have to be dedicated somehow. Graham Smith, you know, people which have the background, they can do this, and they should do this. Very shortly, time is running out, so I will skip the first thing. That's what I started in my PhD. I did stochastic excitation, one of my few papers which I think nobody cited ever, but I learned a lot on it, and I learned because, you know, I saw with pulses we have dead times and we cannot really see the very broad signals. And then I thought stochastic. I was reading Richard Ernst, and I thought stochastic might be a good way to go. And of course you can see actually dead time free. You detect within the pulses. You can see a T2 of 60 nanosecond, sample with a T2 of 60 nanosecond, but it's not a way to go, yeah, because if you detect within the microwaves, this is terrible. So a new approach is in this same direction, is similar direction, shaping, you know, stochastic EPR is kind of random excitation or phase jumping, pseudo stochastic, and nowadays what we do is we modulate frequencies and amplitudes, and but we don't do it that we detect within the pulses. We detect before or after usually, yeah. And so 2011 we started to build up a home built setup for shaped pulses, X-band. And the advantages are clear again. You know, with our pulses, we have some finite bandwidth, which is not broad enough in our radicals. If you go to optimal control pulses, this was done in collaboration with Steffen Glaser, or to shape pulses, to chirp pulses, then you can get much broader bandwidths. Yeah, you can get gigahertz if your cavity is supporting that. Gunnar has done this with gadolinium, and that is an advantage. And here shown as a Fourier transform. If you do it with a hard pulse, here's the pulse, the zero. If you do it with a hard pulse, with here you see you get the lines of this radical. This is in liquid solution, but you don't get in the right amplitudes. If you go to OCT pulses, you get it right, yeah, and you get a shape of a nitroxide, and you get sifter. You can improve sifter, and you get it working, and you can do DQ3 with going down with your modulation amplitude to 0. Yeah, so that in principle all works, and Philipp Spindler in my group, he has also shown you can then, if the pulses are working so beautifully, if you excite 95% of your spins of a nitroxide, then you can also go to a DQC experiment, and you can go to more pulses, and then you get really some advantages. But and so I make it short in the second part, because this is something probably you have seen already or you are using. All the Bruker spectrometers are now with AWGs sent out. Here, just the last example, which Alice Bowen, when she was postdoc in my group together with another, did. So you can do now these orientation selective experiments in a single shot. Yeah, so you don't do it usually in Peltor. We change pump and probe frequency, and you do this experiment 25 times with different offsets. Now you do it with broad-shaped pulses, and you get all the orientation selective offsets over the whole spectra in a single shot. And you get it with better signal to noise than you get it with rectangular pulses. So that's great. Yeah. But what is the but? The but is shown here. This is just from recent testing of my co-workers in the group. What you see here is in blue what you expect for the pulse. This is a 300 megahertz broadband pulse. Then in black is what you see. If you measure, this is a narrow quartz signal, just change the frequency and step by step recorded. And then you see it's okay, but it's kind of okay, but there are some missing parts which are really terrible. There's a steep ditch here. This is a leakage which we have. This is what was the on resonance frequency. On resonance is 0, but it's not true. The real on resonance was here. And then we have some leakage because we have a homodyne mixing like Brugger has, different from Gunnar's. And what you also see is there is this holes, and the holes, this is just the Rabi oscillation profile. And then you see these holes are kind of following standing waves in our resonator. It's not a resonator. The resonator is much more broad-banded. We used a special resonator, but we have some standing waves. And so if you do it wrong, then with AWGs, what can happen? What you put in is not what you get out. Yeah, and and this is only the pulse, not even the signal. Yeah, so the pulse which your sample sees is already a baked pulse. Yeah, and if the baked pulse is roasted badly, then it will not really your sample will not eat the pulse. Yeah, and it's not so dramatic if you just want to invert spins like a pump pulse. If you want to do more tricky things, it's a problem. So here my summary for shaped pulses. You can get a much larger excitation bandwidth with the same microwave power, but to set up really that this is really flat and that this is really good is more complicated. Yeah, and what is nice actually is that my experience with the AWG shaped pulses, with the modulator shaped pulses, have a much better shape than if you do it classically with pin diodes. Yeah, so they don't have these artifacts ringing in, ringing out, and this is good. And this is so even for rectangular pulses, you should use your AWG. It makes nicer pulses, because this ringing in, ringing out is not only an artifact of the detector. This is really what your sample sees, and it has a beautiful phase accuracy. And that's again also for rectangular pulses. This is very helpful. You can, for example, do a multi-quantum filtering, which I didn't talk about today, but we did it with narrow samples with rectangular pulses. In principle, you have an improved performance on multi-pulse experiments, but it's hard work, to be fair. Yeah, it's not routine yet, I would say, at least not in our lab. And real 2D experiments are possible. Real 2D means one time domain is for free, like in NMR. Yeah, that's the dream of EPR. Usually we don't have this, and we can have it. We can make a real Fourier transform of our radical, and this is beautiful. Yeah, if you have orientation selection, of course. If you have information into that. If there is no information into it, then of course it's useless. If there is some spectral resolution into it. It has a beautiful high potential at high magnetic fields, but it is not trivial to implement. Yeah. One of the big things is the spectrometer. You know, NMR people, they have the shape pulses forever. Jeffrey Bodenhaus and Lynn Emsley and many others, they were implemented them many years ago, and now they are routine and you are using them. EPR is different because we rely much more on the instrumentation, and we not only the resonator, but also, you know, all the waveguides going in and all the waveguides going out, and each part, each component which is sitting in there, even the protection switch does something. Yeah, and all that. It's not so that makes it really complicated. So I think I'm optimistic. I think for example, to avoiding these standing waves, a bimodal resonator in transmission might improve the performance dramatically. And so you have to think about new resonators, a new spectrometer for an AWG, not just implementing an AWG, which is cheap. You should think about a real dedicated instrument about it. And and you need good calibration procedures, how to set your pulses, because what does it mean to set a pi pulse? Yeah. Do you want to have the maximum signal over all your nitroxide, or do you want to have for all of them almost the same turning? These are two different aspects. It's not the same. Yeah. If you optimize for maximum signal, you don't optimize for flatness of the pi inversion. And so we need new procedures to set up experiments. maybe even procedures how to take into account what the spectrometer is maybe not performing optimally, and then optimum control theory pulses might be really strong to help for that. Finally, that's my conclusion. The AWG has to be the heart of the pulsed EPR spectrometer, not just an add-on. Yeah, if you make it as an add-on, it will work, but it will not work very convincingly. Heart means, our heart is not beating. It doesn't look like the blood is coming and then says, okay, let's beat in the same tact. It goes the other way around. The heart gives the frequency, yeah, and all the others has to follow it, and not the other way around. So the AWG has to be the central unit of the whole spectrometer, and I'm looking for that. That's not existing yet, neither commercially nor really handmade, and so I think that is something. There is a lot of improvement there. Good. I should finally thank. I should thank many people, but I just want to thank three people. Andre, because he allowed me to show his beautiful new work on DNP, which should be given with other talks, of course, and then Vasil and Burkhardt, which helped a lot on all these instrumentation aspects I showed you. And of course, there were also many co-workers, postdocs in my group, and PhD students in my group. Some of them you might know, some of them might be even here, and which worked on applications, but also on instrumentation, and helped to improve our own setups. And then here I only mentioned collaboration partners, which were crucial for what I showed now here. Snorri for these rigid spin labels. Sun, we worked a lot together with high field EPR, but also with the manganese application. Steffen Glaase for the optimum control pulses, and Steffen Stoll for this out of phase pattern now. And I thank you for your attention. Sorry for going a little bit over time.
Thank you, Thomas. That was it was really amazing, actually. Give me a couple of goosebumps to think about where we come from, and also like where the future lies. And I did like your analogy with the heart, the AWG being the heart, giving the rhythm or the frequency. I did appreciate that one.
Yeah.
Now we come to the most important part of any seminar, which is of course the question session. So for that, please just raise your hand, and then feel free to talk, or in case if nobody's speaking, please just speak up. While we're waiting for people to ask questions, why don't I just go ahead and just ask you like an optimal question? And now that we have all this new technology coming up, it feels like one other part which I think is still great and which we still can improve is actually port sequences. I mean, if we were looking, a DO sequence, fine, we have 4 ports, it's fine. I add another ports, I get the T1. But in reality, we should be porting at 30, 40, 50 ports, whatever we want. I think there's also like a giant gap where we can still delve into. But I guess we need applications towards that, right? What do you think?
Yeah, so I give you, because this was a little bit of this historical. Sorry for that.
Yeah, no, I appreciate it. It was awesome.
So I give you an historical answer. I think that was my first Rocky Mountain conference. I went, and then Arthur Schweiger was there, and he was developing pulse sequences all the time, and he was always very fair. And he said, this is a nice pulse sequence, but don't use it for a serious application because there are so many artifacts. And what he said, Thomas, in EPR, we should always aim for the smallest amount of pulses because all our pulses, even if we call them pi half or pi, they are not pi half pi, they are just arbitrary angle pulses. And that means if you make more of them, you make more artifacts. I think that was true for a long time. But again, with shape pulses, if we get them really good running, then we should be away from that. And I think for tritial reticles, we are already away from that. Yeah. And so that means then, I was always jealous looking at these NMR sequences. And I think in EPR we can, but we have to be able to manipulate our spins homogeneously. Yeah. Otherwise, you create a lot of garbage. If you lose with each pulse, if you lose 70% of your spins, then of course you can count down how many pulses you want to have. I think that the arbitrary wave generated shape pulses in the future they might open up new doors for and then then we have, because magnetic resonance is so strong, our coherences, they survive for long enough. Yeah, OCT pulses are not so long. Shape pulses, just chirp pulses, they are rather long, 200, 300 nanoseconds. They have to be long to be broadbanded. But and then you cannot make so many because T2, yeah, you can count 2 microsecond T2, 200 nanosecond the pulse. How many pulses can I have? But if you make an OCT pulse with the same performance, it has only 30 nanoseconds or 40 nanoseconds. So then you can think about really tricky experiments. I think in the next 10 years this will come.
I think so too. I'm actually quite excited about it, and more interestingly, like maybe we will certainly catch up to NMR, maybe even overtake them. But that means,
our case is totally different from NMR. Yeah, it's different from solid state NMR. It's different. It's more close to solid state NMR. It's rather far away from liquid state NMR. We should be always aware because our spectral resolution is by far not what a liquid state NMR people have, and then our bandwidth is much more dramatic. But I think there is something to learn from the solid state NMR people, and there is also, of course, again, solid state NMR people, they know about probe heads. Liquid state NMR people, they don't even know about probe heads anymore because they don't worry about it. It is all solved. In solid state, they worry because of the rotor and getting smaller rotors and if they want to get microwaves in, then of course there is a lot of things to do. In EPR, we have to think about it. We have to think about the technical part, but also on the method part. Yeah, that's true.
Right. Anybody else has some questions before I continue asking? Please ask away. Okay, well, while we're waiting, why not? Quick question. What do you think about so what do you think about like applications? Obviously, we're already applying a large quantity of instrumentation and experimentation towards biological and towards inorganic chemistry. What do you feel like where there is another opportunity? I mean, right now, I guess quantum information technology is like one driving example. Where else do you think EPR can go where no one has gone yet? Kind of ideology.
So, of course, I'm not really the expert to say that because there were others which are working in this. Here in Frankfurt, I came in the surrounding with a lot of collaboration partners from biology. So all our applications are driving for RNA, DNA, membrane proteins, in-cell EPR. And that is a big field. And most of us are working in this field. But of course, the pulse techniques, and especially also this more advanced manipulation of spins is now developed by other peoples in these other fields. There are groups working in spin technology. There are spins working in battery work. There are people working in different fields. And there are beautiful applications now from people working on organic battery materials with pulse EPR, not CW. CW was already established for it, but now going in with pulse EPR, with high field EPR into that. So I think this is a big future.
Right. Actually, Maxi Rösler was asking a question. She's asking, can you say a bit more about the quinone binding through relaxation study at 100 Kelvin? Grimaldi et al., I think. Thanks for the great talk.
So that was not only I showed one transparency from Stefan Grimaldi. He was PhD student. My group is now in Marseille, and he was working on quinol oxidase and the quinone in the quinol oxidase, and looking for how is it located inside of this pocket. But we did also published work of QA in photosynthetic reaction centers on that, and looked into it. And so what you do is you analyze. As I said, Sergei Zuba did a lot of work on that at X-band. If you go to high field, you get a little bit more information because now you can distinguish also the X and Y component. And of a nitroxide, for example, or of a quinone, and what it helps you, you analyze now the T2 is coming from the vibrational dynamics at 100 Kelvin. It's still not totally frozen, so that means there is slow motion of it, and this slow motion is affected now if you how the hydrogen bonding network to the surrounding is. So if it is bound on both sides, it's a one-axis rotation. If it's bound on one side, it's a cone with a one-axis rotation. So you can learn a little bit about these details. Yeah, it's a very specific application, but Tsuba is doing this with spin-labeled nitroxides in membranes, and again, you learn about the local dynamics.
Actually, I'm actually quite a big fan of what you said during your talk. You mentioned that, well, if you keep it in a solution, we're going to get an average, and that's normally what we can see from many experiments, actually, right? An NMR or whatever fluorescence, we always see some kind of average largely. Fluorescence maybe not always, but when we freeze it, it's very nice. You can actually see the orientation. You can actually take both in conception to each other and then get, well, I'm gonna get the ensemble, and then in solution, well, I'm having the average, so I know what rate it has to sample almost. So it's a very nice thing to combine together, but that also gives the pulse EPR, at least in the frozen case, quite a lot of power, because we can look at the ensemble. We directly look at it. It's a direct observation, no indirect relaxation studies or anything like that. It's really strong. I like it a lot.
You know, Thomas, we should really be proud on that. For a long time, I was excusing always to make measurements 100 Kelvin, where there is no dynamics. And people told me, don't talk about dynamics, talk about conformational flexibility, because you cannot measure dynamics. But then we did this experiment on a double-stranded DNA at room temperature before we have analyzed the breathing motion of double-stranded DNA. And then at room temperature, we could do this experiment in the way like Elena Bakanskaya did it, immobilizing the DNA with a nucleosynth. So the DNA was immobilized, but at room temperature. And then suddenly this internal motion is gone. It's gone. And we were shocked in the beginning. But then we realized if we take the MD and we just average now over the time scale of the dynamics, then we get exactly the traces which we see. But all this beautiful information about conformational dynamics is lost. So Fred people can never see these sub-microsecond fast dynamical motions. They will average. Yeah, NMR people also. So NMR people, if you do it tricky, they will not average, but they have to do it tricky. Think about relaxation and the time scale. So fortunately, we don't have to think about time scale. We have to think, to be fair, I think Jack Fried has seen that. We have also seen it once. It could happen that if you have a motion at room temperature which is driven by entropy and Gibbs energy. Yeah. Now it might be because because now you go to lower temperatures, it might be that you go into an energetically favored state, which a different distribution. So it might be, but then again, you learn something out of it. Yeah. But you have to be a little bit careful, yeah. But in most cases, in proteins or in RNA, DNA, which are very flexible anyway, the potential is so flat that at low temperatures you see almost the same distribution than you see at 50 Kelvin.
I agree.
And that is beautiful. So because we can then really see. We can see what the crocodile is doing. Yeah, you know, we are not. It's not just fixed like this. It's going up and down and up and down, and we see all the states.
I agree. Sorry, we have to move on. Like Marat Gufrov was asking, what's the lowest temperature you can go at your DMP setup?
Not really deep. I think Vasil is working on it now to get it lower temperatures, because we want to see the transition for the solid effect going from a liquid to a solid. Something will happen there. At the moment, the reason is because if you cool down the probe, the microwave transmission line is not very well isolated, and then we freeze something in, and then microwave doesn't transmit anymore. So this is under development at the moment. I think they can go, let's say, like -10 Celsius or so, but not really deep down in temperature.
Vinet Talakotor was asking, You mentioned the standing waves. Where are they forming in the resonator? What are the
Good question.
disadvantages to it?
Good question. You know, for this figure which you showed in the end, we were, you know, you can of course from the oscillation period you can fix out what is the length, yeah? Because you have let's say in a dielectric waveguide with the semi-rigid dielectric waveguides, you have 0.7 of light speed, and so you know exactly the standing wave you get. But we have not one frequency; you have a couple of them, so it's really difficult. You get one connector, each connector. Let's say each connector, the connector to your probe, the connector to your TWT, the connector to your detector. Everything has a standing wave. None has a USVR of 1, and even small effects there will pile up. And to avoid them is not trivial, but probably Graham or others can, if they seriously work on it, they can do that. But you need really people thinking about it seriously. And as I said, I think one way which is really bad at the moment, we are looking in reflection. If we look in reflection, there is a standing wave in and there is a standing wave out. You should correct for the standing wave in for your pulses, but you should not correct for the standing wave out, because that's not what your spin is seeing. Now, how do you know which is the standing wave in and what is the standing wave out? So better to have a transmission where there is no overlap of standing wave in, standing wave out. Or some really clever solution where you have no standing waves at all. Probably that would be the best. And but you know, if you just want to invert your spins, they make a little bit of holes, but it's not so bad. If you go for a pulse, not going from Z to minus Z, but from X to minus X coherences, this becomes traumatic. Then you become phase errors and you become terrible errors, and it's very difficult to correct for them. It's very difficult.
Let's see. Oh. Oops. Hold on. Then further, he was asking also how challenging is implementing the interferometer. The interferometer you presented.
I just mentioned this from the Ukraine-built interferometer, where you have a second pathway and you have something short, and then you have now not a 50% coupler. It's a mirror, but the mirror is something like 1% goes to the detector and 99% goes to the sample. And then the reflector gives this other 1% coming back, and then they interfere to 0 so that you can survive the big power coming from the gyrotron. Now, still, this is critical, because if something happens within the experiment, your interferometer, for some reason, displaces some micrometers, you destroy your microwave detector. Just as a joke, that's what we're doing at the moment regularly with Bruker low noise Q-band detection amplifiers. We destroy them like fuses. Every 3 weeks we get a new one for free from Bruker because something is going wrong. But that's not really what you want to do. Yeah. So it works. I also showed very briefly, I didn't mention it, this bimodal cavity, which I used for this Fourier transform EPR, where I get 30 dB decoupling from the pulses, which is very robust, and which actually really helps to bring down the power of your excitation to a level where you can handle it more easily with the detector. And I think, you know, Ximenas Mantas is going, and others are going, John Morton and others are going to do this now, increasing sensitivity by going to a high sensitive low temperature detector, low noise detector, and cooling down the resonator. Again, such approaches will help a lot. But of course, you know, as everything, if you do something like that, it makes the setup a little bit more complicated. Let's say it this way.
Great, thanks. Well, since we're waiting, maybe I can ask one more question before we go to the end. Thomas, I have a question. So we talked about instrumentation, we talked about application. Of course, there's also another part to it, which would be the software development and making it available. Because I mean, the ultimate dream would be that every lab in the world should have at least a CW machine sitting on the bench somewhere, right? And then, of course, people need to use it in a way. What do you think? How do you feel that the software development is coming, or the data analysis for that sake? What do you think about that?
Yeah. Yeah. Uh, uh, it depends. The G-band spectrometer we are running with the SpecMan from Boris Apel, and that runs very beautiful and easy to handle. And you program, of course, and our home-built AWG X-band also is running with home-built software, which is driving the AWG. Of course, all these softwares are. And then many of you run Bruker spectrometers, and then the software has some other restrictions, I would say. Bruker is aware of that. Bruker wants to improve this and has to improve this. As I said, I also told this Bruker, you have to really make a revolution with an AWG. You should not make just an adaptation of your existing spectrometer to an AWG. You have to design a totally new one. So maybe Thorsten or others are going to do that. And of course, for good software, this is always tricky. I'm not really a specialist on it, but when I showed you these old spectrometers, I was building all my spectrometers on my own in the beginning because there was no Bruker pulsed EPR at that time. There was Peter Höfer as a PhD student with Michael Mehring, and we were competing against each other. And I had a student from informatics coming and writing the software, and he was writing 1 year the software, and then he was very proud and he said, this software is foolproof. And then I started to fool around, and then immediately it broke. So that's just again an old story. And now this is of course better, but it's not trivial. To have a software which allows you, if you have a great new idea, to immediately implement it, and not hinder you, right? So that you have to do 2 weeks of programming to try an experiment. This is the dream, and hopefully at some point we reach it. And but again, you have to, similar like with I'm more the expert on the hardware, so I know the AWG has to be the heart, but the software is the brain. And again, you need somebody who knows about how to make the brain that he can really do everything immediately and fast. And that is again a major task. So we have to wait.
True spoken. Very well. Thomas is asking a question. Go ahead.
Hi. So I have a question about the DMP and about the solid effect in liquids. So now you're working at 9.4 Tesla, and you're seeing solid effect with a kind of large radical and large molecules. If you go to higher field,
large molecule, let's make it reasonable. A BDPA or a trityl, and a large molecule can be a short DNA, or it can be a ATP, in water. This is large enough.
Exactly, this is large enough. But do you think that,
let's say each biological molecule will do it?
Okay. And do you think that going at higher field, you would see the same solid effect on smaller molecules, let's say? Right?
Small, slightly, but I think the big step, the solid effect observed in liquids, we are not the first, or Andre is not the first. Kerstin Münnemann and Stefan Stapf and Spies, Wolfgang Spies, they have seen it already at X-band. Now at X-band, what you miss is the spectral resolution. And then you have to go to really high viscous solvents, and then you compete between Overhauser and solid because they overlap. And then you don't see both of them in a good way, because these are two sides of the medal. You can have either Overhauser or you can have solid. And the advantage, if you go, let's say, at least to 400 megahertz NMR frequency, is this overlap is over. It's 400 megahertz away. So there is no Overhauser 400 megahertz away from the EPR line. And At least not for the radicals with the radical has not to be so big. It has to have narrow lines. That's a good part to it. And for nitroxides, you see an overlap. We still see the solid effect, but then the solid effect overlaps with the Overhauser effect, and it's hard to analyze. And then at low field, you don't have spectral resolution that you see really now the different chemical shifts for the different nucleus you are interested in. And that's important. So you have to go to high field. I think it will work also at higher field. Yeah. At higher fields, what you need is you need high microwave B1. That's what you need, nothing else. And this is, of course, more tough at really high NMR fields to achieve. Yeah. Because yeah, maybe, but it's tougher. Yeah. If you go to really high fields.
Yeah, I agree. I have also a second question, if I can go on, about the high field EPR spectrometer. So you commented on the central role of the AWG. Can you comment on the power that you need? Do you need, like, what's a reasonable output power? Are there ways to improve that? What's your thought?
Say it again. The microwave power for
260 or a high field EPR.
For the solid effect?
No, for EPR spectroscopy. Like what's the
for high field EPR. For high field EPR.
Yeah.
Yeah. So of course, if you have this high power like Graham has, this is beautiful. Then you can go with large samples without a resonator. But you see that even at 260 with Virginia diodes, the microwave power is increasing for DNP. You know, they make a lot of developments now for DNP in solid state amplifiers. So I think up to 260 gigahertz, the microwave power is not a limiting for the EPR, because especially if you combine it with shape pulses, yeah, because this is enough power that you can cover sufficient of your, already now you get pi pulses, pi half pulses of 20 nanoseconds, 30, 40 nanoseconds. So this is fine. And if you go for shaped pulses, you have decent excitation bandwidth and decent detection bandwidth. So I think if you go to higher frequency, it becomes tougher. Yeah, that's clear. Yeah, but at the moment we don't have really pulsed EPR running at higher frequencies than I think 260. There was one demonstration experiment many years ago in Grenoble, still 540 gigahertz pulsed echo detected EPR with far infrared lasers. Yeah, 2 far infrared lasers coupled Luc Brunel doing this experiment, and Hans van Tol, who is now in Tallahassee. But up to 260, I don't think for EPR the microwave power is limiting. Let's say at least if you combine it with some shaping. Yeah, shaping is, of course, as I said, now you can do phase modulation, and in optimum control theory you can get good bandwidth even if you only make phase manipulation and not amplitude manipulation.
Okay, thank you.
There's one last question from Chukyu Zhu. Maybe you can read it. Hello, Professor. May I ask you an experimental question? On the EPR of continuous wave, there's a peak at room temperature and a peak of opposite phase at 90 Kelvin. Is it possible that room temperature is a peak of monomer free radical and low temperature is a peak of free radical dimer? Can I test this hypothesis with transient EPR at room temperature and low temperature? Opposite phases correspond to spectral lines of different microseconds.
Maybe this refers to these out of phase signals which I was talking about, but this out of phase signal you should only you will not see them under regular conditions at Q band. So no, don't worry. If you measure at 50 Kelvin and Q band, you will never see that. So this is something exotic. You have to go to 4 Kelvin and 200 and 180 gigahertz. And so I don't think that will answer this artifact which you see. So there might be something else, but I cannot really answer it on this level. Yeah,
that's great. That's all right. All right. If there's any more question, otherwise I want to. Oh wait, sorry. Juju Zhao is asking. Yuji, do you want to ask them, Dr. Prisner?
Hi, Thomas. Very nice talk. Thank you very much. I just have a follow-up question from Thomas Orlando's question. So how does the Overhauser DMP enhancement increase with the B1 at very high power, for example, at W band with kilowatt? Because before we were seeing some experiments that we get enhancement in initially until about 100 kilowatt, 100 watt, and then it doesn't goes up more. So is that what you would expect from most of the Overhauser DMP sample, or there's something that is happening?
So if you saturate your EPR transition, that's all you can do. And then you have to calculate, of course, the coupling factor. And the coupling factor means how then the saturation factor is optimum, and the coupling factor is usually not depending on the microwave power. So, and that gives you then a small or a bigger overhouse effect depending on how high your field is and what are your conditions of your molecules. Now, what we saw experimentally, we saw always an increase of our overhauser DNP if you go to higher microwave power. Not because we could not saturate, it's what we learned later on in the beginning. We thought, okay, we don't saturate your EPR transition, but because we heat the sample. And now if you heat the sample, viscosity goes down. If viscosity goes down, the correlation times become faster. If correlation time becomes faster, then of course the overhauser gets bigger. Coupling factor becomes bigger. But that's usually not what you want to do. You don't want to blow up finally your sample. But I have seen before, Marat Gafurov was also here listening, and he did a lot of these experiments, and he got beautiful enhancements of 100 up to 90 or 91. But this was already supercritical hot water and nitroxides in there, yeah? And, you know, these small capillaries, they can exist even at 120 Celsius for some time, and then suddenly blow up, and then it's over. But of course, with this supercritical hot water, you get beautiful DNP. Now, so experimentally, it's very difficult to disentangle the temperature effect, which you, if you change microwaves, and especially if you don't have a resonator, you will always change sample temperature. And then to disentangle, because with temperature, everything is changing. T1 of the electron, T2 of the electron, the dynamics of the between electron and proton, proton T1, proton T2, everything is changing. So then it becomes really tough. Yeah. So you have to find really a good way. So for us, it took us a long time to calibrate temperature, to figure temperature, and to stabilize temperature. The last probes from Vasil, even with maximum power, we get in maximum of 5 degrees Celsius higher temperature than we had before. This is great, yeah. And then you don't have to worry. But otherwise, you have always to think about what you do with your sample, especially in Overhauser. Yeah.
Okay, great. Thank you very much.
I think, Thomas, you're muted.
Sorry about that. Well, that was a great chunk of questions. And most importantly, we want to thank Professor Prisner for presenting and giving us insights and outside, for that sake, to all our beloved technique in EPR. And with that, thank you to Professor Prisner. And I hope to see everybody again. Thank you very much.
And sorry for being so long. Okay.
Oh, that's great. I think you did great. I appreciated it a lot. It was awesome.
Bye-bye.
Thank you very much. Bye.